Assalamu alaikum and a very warm welcome to everyone. This is Geotechnical Engineering. Let's recap back on chapter 3, which is on soil consolidation. So this topic covers 9 subtopics, which is C1 to C6. Now, you have been briefed before that this lecture number 3 consists of 2 parts. C1 to C5 is part 1, okay, whereas from C6 to C9 is part number 2. Okay. As an introduction, you should know what is the concept of settlement. Now, any structure that is built on top of a soil are subjected to settlement. It's a nature thing. And some settlement is often inevitable. It is gonna happen. And some settlement is tolerable, whether we accept it or don't accept it. Now, for example, small uniform settlement of a building throughout the floor area might be tolerable, whereas non-uniform settlement of the same building might not be. If you have a building here and on the left side, the settlement is about 5 meters, and on the right side is also 5 meters. So this is where settlement is okay, means it's settled uniformly. However, if you have another case where this on the left side settles about 10 meters and this one settles only about 1 meter, then it will be a significant effect to the building. And this is called non-uniform settlement because they are differential in settlement. One side here is 10 meters and another one is at 1 meter. Or settlement of a garage or warehouse building might be tolerable, whereas the same settlement of a hospital building would not be because of damage to the walls, ceilings, and so on. Now this one refers to the importance of the building. Okay, a building which is important, such as a nuclear power plant, hospital building, we don't want any movement. Okay, if there's a movement, there's gonna be trouble. Whereas if you compare to a small house or small structure, you can expect some settlement which is okay. So in any event, a knowledge of the causes of settlement and a means of computing settlement quantitatively are important to a geotechnical engineer. Your task as a geotechnical engineer is to have knowledge. How do you have this knowledge? Is from observation. You have a case study, a lot of case study, you observe sites, and then you will actually find the causes of settlement. Okay, and then you will show some numerical presentation on the observation. This is by computing settlement quantitatively. Okay, so in the aspect of soil consolidation at site, geotechnical engineer will go out to the site, observe how the condition, and lastly compute the settlement quantitatively. Okay, you have to have a value on your observation. So that's the basic role of a geotechnical engineer here. Okay, now there are several possible causes of settlement. Okay, these are the general one. Dynamic forces is number 1. Okay, so dynamic forces refers to something like an earthquake, right? Second is changes in the groundwater table. Of course, when you have changes in the groundwater table, okay, so you're going to have some effect on the settlement as well. Sorry. And third is adjacent excavation. Now, what is this excavation? Okay, is when you have a building, okay, and on the opposite side you have an excavation works going on. Okay, let's say you excavate this part area, maybe for a garage or a parking basement or something, and this is likely to cause some effect on the building that is opposite of your building. Okay, so this could be a cause of settlement. And lastly is compressive deformation of soil beneath structure. So when you have this type of causes, you're likely to have a failed soil underneath the structure, which in the end compress the whole thing into a deformed shape. So I highlight only 4 several possible causes of settlement, but there are a lot. This is a case study in China. So as a geotechnical engineer, if you're given a picture, you should know how to observe and interpret what is the cause of this tilting or toppling. Okay, first of all, you know that this is differential settlement, whereby if you draw a simple presentation of settlement analysis, you're likely to have a bigger settlement, let's say 5 meter here, and at back is only 1 meter. Okay, the first observation. Alright, so this is a ununiform settlement, and the building is toppled this way, so likely that this area here, the soil is of soft soil. Okay, this is how you interpret from this picture. And what could be cause of this soft soil is maybe the movement of water. So there are water in here. Okay, and you can see again, maybe this area is prone to rain. So maybe this accident happened after a heavy rain in the previous day or something like that. So everything looks wet, and then yeah, that's basically how you interpret. Okay, now after this interpretation of the photo, you're likely to go to site to make more detailed observation. Okay, this is what you're gonna do as a geotechnical engineer. It's pretty fun. Okay, this is a case study number 2, whereby it shows a collapsed building and other still standing adjacent building. So what actually happened here, if you can look at the next slide. Okay, so this is a schematic diagram of that building. Okay, look at figure number 2. Let's change back the ink. And figure number 2, hollow concrete piles supporting the building. So they have concrete piles in this structure. That's the ground elevation. So everything is in good definition at first. Now in figure 3, this is after excavated soil stockpile on the north side of the building. So this is the north side of the building and this is the south side. So what actually happened, that there's a stockpile of earth over here. Okay, they dug a soil from somewhere and create this stockpile. Okay, so you have a north side, a big loading, and then they excavate on the south part to make a garage or a basement parking. And according to this report, the excavation for the garage did not provide a wall to support the excavation. Okay, so when you dig up here, it should actually provide some supporting over here, because this is already gone. So in this case, they likely forgot, or maybe they didn't design it properly when they excavate. So you have some loading on the north side, and on the south side you tend to excavate without a proper supporting walls to actually support this building. So this thing topples like that. Very simple schematic diagram. Now let's move on to a more detailed study of different type of soil. Now the compressive deformation, which probably the major cause of settlement, generally results from, so here is the main keyword, the reduction in void volume. Okay, the reduction in void volume, accompanied by rearrangement of soil grains and compression of the materials in the voids. Okay, so this is a very basic that you should know what's the mechanism behind compressive deformation. Now, if soil is dry, its voids are filled with air, and because air is compressible, rearrangement of soil grains can occur rapidly. Okay, whereas if you look at when soil is saturated, its voids are filled with incompressible water, which must be extruded from the soil mass before soil grains can rearrange themselves. So this is a nature or mechanism that happens in soil which is in dry state and also soil which is in saturated state. Okay. Now let's talk about permeability. In soils of high permeability, means water can pass through easily, this process requires a short time interval for completion, and almost all settlement occurs by the time construction is complete. Okay. However, in soil of low permeability, that's where water is getting a hard time to penetrate into the soil, the process requires long interval for completion. Okay. The result is that the strain occurs very slowly, thus settlement takes place slowly and continues over a long period of time. Now the later case, which is low permeability, is of more concern because of long-term uncertainties. So let's imagine a soil which is in dry state, okay? And when you read this, you actually can link when you see this photo of a dry soil, okay? What's happening behind the soil, underneath the soil when it's dry, and what happened when it's wet, okay? You get a picture and try to link on the concept that we're being assessed just now, okay? Now let's look at an example of a simple structure of a house, okay? Now this is one land development, okay? So the original grade is shown here, okay? This part they cut it out and then they fill in this part here for the construction process. Okay, a loading, this is the loading, and then the soil taking the loading. Okay, and potential for heave means the soil can expand. And what else? There's a new grade, a new soil coming in on this field area, and that's all about a general picture of a simple structure. Okay. Now, what could possibly be some negative effect from this development? Okay. First, we look on the evaporation. Hot, dry wind and intense heat causes the soil to sink beneath the foundation. Okay, it makes sense. You have a series of different changes in climate, especially in four season country, where at first it becomes hot and then cold, hot and cold, hot and cold. So this creates some instability in the soil structure. So that's why you can see a movement or settlement of this house due to the evaporation of water. Okay, the first is evaporation. Now second is when you have a plumbing leaks. So this one can cause a settlement also in the simple structure. Water from plumbing leaks, so this is a leaking from the plumbing, is often the cause of severe foundation problems. Okay, maybe this one will settle and this one stays. Alright, and the third one is transpiration. This is because of a tree, where tree roots may desiccate or cut through the soil beneath the home, causing the soil to strain. I wouldn't want to blame on this tree. Tree is a good, positive aspect in development. Okay, so it's actually this is the main problem. You have a land, you have a home, you change some natural settings, and then you're gonna blame this tree. For me, the tree is not a big problem. You're the big problem here. Now, if you look at a more overall damage that could happen in a house, okay, if you don't take care of these 4 items here, okay, you're likely to promote a more damage seen in your structure. For example, the first one is drainage. Improper drainage is one of the leading causes of foundation failure. Excess moisture will erode or consolidate and cause settlement. Okay, so that's why a house, you got to make sure that your drainage is properly designed to actually channel the water to its designated place. Okay, so that you will prevent from settlement. Okay, the second is on poor soil condition. So poor soils and its expansion and or contraction contribute to foundation failure. So make sure that your house has a good soil condition. Third, inferior ground preparation. Soft, low-density soils and or improperly compacted soil beneath a home is the leading cause of foundation failure. So this is during construction. So make sure when you plan to buy a house, you should look at the contractor doing this. Let's say land development. Make sure it's a quality type of contractor doing this. And lastly, you have to take care of the inferior foundation construction. Again, this one goes back to the contractor, and the contractor goes back to the design engineer. Means the structural engineer that designed a house. Make sure he has provided sufficient amount of structural members for this house. Okay, so that's all about it on a simple structure of a house. Okay, let's move on further. Settlement of structures on fine-grained soil generally consists of 3 phases. The first phase is termed as immediate settlement or volume distortion settlement. I would like to just stick to immediate settlement for here. As suggested by the expression, immediate settlement occurs rapidly after load is applied. Now, caused by soil volume distortion, immediate settlement is typically completed quickly, and constitute relative small amount of total settlement in fine-grained soils. Now, subsequent to immediate settlement, primary consolidation settlement. So this is the second stage in consolidation. The result of primary consolidation. Now, these are commonly referred to simply as consolidation settlement and consolidation respectively. Okay. Now, this second stage occurs due to extrusion of water from the voids as a result of increased loading. Okay. Now, primary consolidation settlement is very slow and continues over a long period of time. So this is the second stage. And the third stage, now after primary settlement has ended, soil compression and additional associated settlement continue at a very slow rate. Let me change the highlighter. Oh, this one better. The result of plastic readjustment of soil grains due to a new change stresses in the soil and progressively breaking of clay particles and their interparticle bonds. This is when you talk about more detailed aspect of the material. Now, this phenomenon is termed as secondary compression, and associated settlement is termed secondary compression settlement. Okay. Figure C1 illustrates the 3 phases of settlement as a function of time. Now, let's look at this figure. So this figure C1, 3 phases of settlement for fine-grained soil as a function of time. Now, when you look at the figure of a graph, you have to make sense out of it. So first you have on the x-axis is the time. Okay. In this case, it's the time of the settlement that occurs. So 3 stages is defined here. So the first one was stage 1, which is immediate settlement. Second stage is primary consolidation settlement. And lastly is the secondary compression settlement. Okay, 3 stages of consolidation is defined in this graph on the x-axis. All right, does it make sense? So the time increases, okay, and if you look at the settlement on the y-axis, the settlement is actually decreasing. Okay, the value of settlement is decreasing, and at the point at some time it actually become constant here. Okay, so immediate settlement, we have a bigger settlement, and when it goes to the second stage, primary consolidation, the settlement decrease. Okay, So as it reaches the third stage, it becomes lesser and then become constant. So this is the nature of consolidation with 3 stages from this figure C1 with respect to the function of time. Now let's move on further. In analyzing clay soil, okay, clay soil over here, it's my highlighter again. Okay, still here. Now in analyzing clay soil for consolidation settlement, one must differentiate between 2 types of clay. Okay, for this course, there's only 2 types of clay. One is normally consolidated clay and the second one is overconsolidated clay. In the case of the first one, okay, which is normally consolidated clay, the clay formation has never been subjected to any loading larger than the present effective overburden pressure. Okay, please take note of this term, effective overburden pressure. So this is the case whenever the height of soil above the clay formation has been more or less constant through time. So you have a constant loading when the time passes by. So this is your clay layer. So this is the loading on top, okay, and the loading on top is actually constant throughout the time. So this is a normally consolidated clay. Now with over-consolidated clay, the clay formation has been subjected at some time to a loading greater than the present effective overburden pressure. So again, this term, effective overburden pressure, this occurs whenever the present height of soil above the clay formation is less than it was at some time in the past. Now such a situation could exist if significant erosion has taken place at the ground surface. Due to erosion, the present height of soil above clay formation is less than it was prior to the erosion. It might be noted that over-consolidated clay is generally less compressible. As it will be discussed under this chapter, okay, I'm going to show this later, the analysis of clays for consolidation settlement differs somewhat depending on whether the clay is of normal consolidated or over-consolidated. Let's move on to subtopic C2, immediate settlement of loads on clay. Alright, immediate settlement, very fast, and concentrate on clay, very fine particles. Now as mentioned earlier, the immediate settlement occurs rapidly, perhaps within hours or days after load is applied. It is caused by soil volume distortion, and it is usually constitutes only a small amount of total settlement in fine-grained soils. Immediate settlement may be estimated based on the linear theory of elasticity. This is a basic concept, and equation C1 is applicable. So this is how you calculate immediate settlement. Okay, this one is given as immediate settlement equals to, so shape and foundation rigidity factor, and it's also equals to Q, which is magnitude of evenly distributed load, and B, width or diameter of foundation. Again, you have your constant mu, Poisson's ratio, and also another constant, which is your undrained elastic modulus of clay. Okay, so everything connects to immediate settlement. Now EU may be evaluated using the result of undrained triaxial compression tests performed on undisturbed soil samples. So EU can be taken from laboratory tests. The value of EU frequently lie in the range of 500 Cu to 1500 Cu, where Cu is the soil cohesion shear strength as determined from the undrained test. Okay. The lower range is for clays of high plasticity and where foundation loads are larger, while the higher range is for clays of low plasticity and where foundation loading is low. Now, if the results of undrained triaxial compression tests are not available, table C3 can be used to estimate appropriate values of EU. Okay, so 2 ways in determining this constant. is either from a laboratory test triaxial or from a established table, which is in table C3. Okay, this is table C1. Now this is values of CS. So CS can be taken from this table. You have different types of foundation with respect to dimension of this, and then you get the value of CS. This is table C2, the value of CS for foundation on clay, soil of limited depth. Okay, you have a circular foundation here, and then the CS respective of its depth to width ratio. And lastly, this is a table to actually get the EU constant. Okay, so this is pretty easy when you don't do the test. You have different clay consistency, soft, medium to hard, cohesion, and then the value of EU. So you gotta make decision making when you use this tabulated established chart. Right, let's recap back on consolidation tests. This is subtopic C3. Alright, and you are likely to refer to ASTM D24354. More details on step-by-step guide on consolidation tests. Or you can look at Soil Properties Testing, Measurement and Evaluation, 5th edition by Liu and Abbott 2003. So two types of guidance you can look or search to look on more detailed information on consolidation tests. Now let's just recap back on this. So this is the apparatus for your consolidation test. Okay, you're gonna put soil over here, and then you're gonna apply loading on top of here, and you're gonna read the dial gauge. Alright, and you're gonna have a series of loading and unloading of loads. Okay, so this apparatus is known as consolidometer. Alright, so if you look at a more detailed sketch inside this specimen, you have a soil sample is being put between two porous stones. Okay, so water can pass through up and down as the consolidation takes place. Okay, so everything has been briefed to you, and this is likely a graph that you can come out from the test. Okay, in the x-axis, okay, it's the time, and in the y-axis is the deformation. Okay, so as time passes, the deformation becomes lesser, and then you're gonna define the 0% consolidation, 50% consolidation, and 100% consolidation respective to its deformation and time as well. So this is figure C3, dial readings versus log time curve. Okay, so please take note of this term, effective overburden pressure and net additional pressure. Okay, so this is a step-by-step process that you have conducted previously in your lab. 1 to 8, 9 and 10, 11 and 13, and so on. And you've been also presented with a simple formulation, the coefficient of consolidation CV. Okay, let's just skip this one. So this is another graph representing void ratio versus logarithm of pressure. So you have your void ratio here and pressure here. So as pressure increase, the void ratio becomes lesser. So it makes sense is if you have more pressure, the water will come out, so your void becomes smaller. This is when loading takes place, and when it's unload, you have this rebound line over here. And this is another output from the consolidation test, where it is the coefficient of consolidation versus logarithm of pressure. So you have a connection between CV and pressure. So in basic aspect of soil consolidation, you have to come up with 3 items here. The first is the E log P curve. Second, the CV versus log P curve. And lastly, the initial void ratio of the soil in situ. Now all of this is important when you are designing your foundation later on. So you got to carry this information to your foundation design. Now let's move on to C4, normally consolidated clay. As we've been presented earlier, we have 2 types of clay, normally consolidated, and the second one is overconsolidated clay. Now in this subtopic, we're likely to classify whether this clay is of normally consolidated or overconsolidated. Okay, it's very simple. It's just a determination from a graph. But you have to take care of some important terms here. Effective overburden pressure, which is denoted by this figure here, this symbol here, small p with an O. Okay, let's straight jump to this figure over here. So figure C10 is a typical E log P curve for normally consolidated clay. Now, why is it normal consolidated clay? So first step is to establish this chart. Okay, you have void ratio on the y-axis, and on the x-axis you have the pressure in log scale. You got to determine the initial void ratio and the pressure. Okay, P0, which is the, so I've briefed you earlier, P0 is effective overburden pressure. Okay, so you gotta make a line, E0 and P0 up here, and then it's being denoted by A. When it intersects, the point is called A. Alright, the second step is to make a straight line from the bottom. Okay, this dotted line here, and whenever it intersect with this line, okay, so a symbol of B is given here, so this point B is given here. Okay, so if B falls at this side of A, means if I'm looking from here, it's falling at the left side of A, right, my left. Okay, so this is when the clay is normally consolidated clay. So this is how you determine the first type of clay, when the B point is at the left side of A from this chart here. Okay, so this is how you determine. Okay, now the same process for overconsolidated clay. I think you can guess already. If the B falls on the left side of A, is normally consolidated. If you are having a vice versa, if B falls on the right side, it's actually, yes, very good, overconsolidated clay. Very simple. So if you follow the steps, B falls on the right side of A, so this is a overconsolidated clay. So based on this graph, void ratio versus pressure, you just point the B, or define the B, and whenever it's positioned in its respective left or right side, that is when you know what type of clay you're going to deal with. Okay, just from this side. Okay. Okay, moreover, for overconsolidated clay, you can also find the maximum overburden pressure. Okay, you have a step-by-step process. Okay, again, you have to define I think you gotta define this line first, GH, first step, second step, and then this step. So in the end, K. Okay, so please read this and find the step-by-step process to get the maximum overburden pressure, which is denoted by this symbol here. Okay, right. The overconsolidated ratio, OCR, can now be defined as the ratio of overconsolidated pressure to present overburden pressure. Hence, the OCR is used to indicate degree of overconsolidation. Okay, we're going to look more into this in the later subtopic, where this is an important term when it comes to your foundation design. So that's the end of part 1. Thank you very much.